Kia ora koutou, welcome to this next video where we look at energy changes. So energy changes in relation to a chemical reaction. If we were to have just a sample, A plus B goes into A and B, these being the reactants and these being the products. With most chemical reactions, nearly all chemical reactions, there will be an aspect of heat that either gets released in the reaction or absorbed for the reaction to occur. So what we can do is we can show heat as being either a product or a reactant. So, for example, if we had two reactants that came together to form a product and heat, that could be an example would be if you had fuel and oxygen, so maybe methane or wood, plus oxygen. So if A was methane or wood or something, and B was oxygen, that would go in to produce a product or multiple products, carbon dioxide and water. We also know that we get heat as a result of that reaction. For other reactions, probably less known to us, we can sometimes have heat which is part of the reactants effectively. So I'm sure a lot of you will have done the reaction between vinegar, so an acid vinegar, and baking soda. And you know that it fizzes up and you get carbon dioxide produced as well as salt and water. What a lot of us won't know is that if you do that reaction, the temperature actually decreases. So for that reaction to occur, heat from the surroundings of the reaction gets brought into the cup or whatever whichever vessel you do the reaction in, heat will be absorbed. So you can give that reaction a go. The temperature change, if you do enough of it, the temperature change is large enough for you to actually be able to feel the glass and it will be cold. So there are two types of reactions that we're going to be looking at with this energy changes. The first type of reaction is a reaction that absorbs heat, and the second one is a reaction that releases heat. Before we go into a bit more detail about those different types of reactions, we're just going to look a little bit further into the use of this term heat, which is very familiar to us. For these energy change reactions, we actually use a different word, which is called enthalpy. So it might seem a little bit unnecessary to be using this word, but as you go further into chemistry, you'll understand that we can't just use heat. Enthalpy needs to be used in place of it. But for the purposes of level 2 chemistry, enthalpy equals heat. So you don't need to think too much about why enthalpy is used. We just think of enthalpy as the heat. We can't measure the enthalpy of reactants or products in itself. All we can do is we can have a look at a reaction. We can say we've got reactants that turn into a product and heat has been absorbed, and we can measure the amount of heat that gets absorbed in the reaction. Or if heat is produced, then we can measure the amount of heat that gets produced. So enthalpy, so this is the defining condition. When you've got a reaction that occurs at a standard pressure, at a constant pressure, the enthalpy is the same as heat. So if the pressure was to change, which would only happen if you had a really closed system, then we wouldn't be able to use this enthalpy anymore. But generally, most reactions that we do, if you think about us doing a reaction in a beaker or something like that, there's a standard, there's a constant pressure around us, and that pressure doesn't change as a result of a reaction happening inside of a beaker. So we can normally assume that the pressure of a reaction remains constant, and in those situations, the heat released or the heat absorbed is equal to the change in the enthalpy of the reaction. So with that said, we can now look into the two different types of reactions that we were talking about, either heat being absorbed in a reaction for the reaction to occur, or heat being released. So we will look at, first of all, the reaction of heat being released. So what we'll do is we'll draw a graph. This is a graph that you'll see often for this topic. So we've got on the y-axis, we have got change in enthalpy. So remember, change in is the Greek symbol delta, which is just drawn as a triangle, change in enthalpy. And enthalpy, the symbol for enthalpy is H, capital H. So we've got change in enthalpy on the y-axis, and then we'll have change in time along the x-axis. So if we're to look at a reaction where we've got the products have a certain enthalpy, we can't directly measure this enthalpy. We can only measure the change in the enthalpy with a chemical reaction. But let's say we've got the reactants that have an enthalpy that's about here, so we won't see any particular values on this y-axis. And the reactants then turn into products, so we need to input a little bit of energy for the reaction to occur. If you think of lighting a match or using that lit match to light a candle, you need to uh, first of all input some energy for that reaction to begin taking place. So fortunately, a candle won't just spontaneously combust. We need to first of all provide a heat source to the candle, and then it will, once it starts combusting, then the heat that gets released is able to continue the reaction going. So what we have is the enthalpy of the reactants is here, the enthalpy of the products is here, and we have what is called the change in enthalpy, is the difference between these lines might be slightly approximate, but this lines up with the products and this lines up with the reactants. We have what is called the change in enthalpy. So that's delta H. So what I should have done actually is not put the triangle on the y-axis because this is just the enthalpy. So we're measuring the change in enthalpy by the products. So the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. So because the enthalpy of the reactants is greater than the enthalpy of the products, we're going to end up with a negative value. So this change in enthalpy for this reaction where heat is released is going to be a negative value. When heat is released, the type of reaction that we get, that we call it as an exothermic reaction. So that's the second word that we're learning for this video, is that when heat is released in a reaction, we call it an exothermic reaction. The other thing that we can calculate from this graph is this little bump here. So let's say that's equal to about there. That is called the activation energy. So that's EA. So the energy required to initiate a reaction is called the activation energy, and that's shown there. We'll now go straight into what is a reaction where heat is absorbed in the reaction. So I'll just get rid of these lines very quickly. So if heat is absorbed, that means that the enthalpy of the products must actually be greater than the enthalpy of the reactants. So heat is being absorbed from the surroundings to increase the enthalpy of the reactants to reach the enthalpy of the products. So you end up with a graph that looks something like this. So we've got the reactants here, the products there, and the change in enthalpy is the difference between this line here and this line here. So that's the change in enthalpy, and it's still the enthalpy of the products minus the enthalpy of the reactants. So because the products, the value of the enthalpy of the products is greater than the value of the enthalpy of the reactants, so this is going to be a positive value when we have this reaction that absorbs heat. And the activation energy of this reaction is taken from the top of the peak there. This is the energy that needs to be input for the reaction to occur. So this is the activation energy. The name of this reaction, so we learnt that a reaction that produces heat is called an exothermic reaction. A reaction that absorbs heat is called an endothermic reaction. So quite similar names, endothermic and exothermic for one that releases heat. Those are the main points that we need to introduce in this topic. We'll look further at energy change calculations for reactions in the next videos. Thanks very much for watching. Like and subscribe for more videos. See you next time.